Hi everyone, welcome to the third research challenge check-in. So our speaker for today is Kurt Gurley, who is a professor of civil and coastal engineering at the University of Florida. His primary research area are in wind effects and residential structures, as well as stochastic modeling of extreme winds and structural resistance. He's also an associate editor for ASC Journal of Structural Engineering, the interim director of the UF Engineering School of Sustainable Infrastructure and Environment, and also an associate director of the shared use UF-NSF NHERI Wind Hazard Experimental Facility. He has over 20-year research career and has secured over 20 million in funding from state and federal agencies and has published over 80 peer-reviewed papers in his research field. Join me in welcoming him.
All righty. So thanks, everybody. My name is Kurt Gurley. I'm at the University of Florida in the Department of Civil and Coastal Engineering, and I've been a co-PI on the NHERI facility, the wind engineering facility at University of Florida. This is the boundary layer wind tunnel. Just a little advertising for us. There's a schematic of the boundary layer wind tunnel, sort of traditional, but has a lot of automation in it. Makes a higher volume throughput for research and a sense of what it looks like on the inside of scale. It's 6 meters wide, 3 meters tall. If you have any interest or questions about this facility, just make sure you get with me whenever you like. So I'm going to talk about defining projects in hurricane hazard research, but I want you to think because I'm going to obviously use wind as my medium to paint with because that's my area. But it could be any hazard, it could be any challenge. It could be seismic, it could be flooding, could be hurricane, it could be agricultural, right? So the basic concepts that I'm introducing you to, feel free to plug and play your own expertise as we kind of go through. And I shouldn't take too long. This is about 14 slides. I intended this to be interactive and to have time at the end for discussion. So by all means, I'm probably going to be prompting you for input and questions along the way. So just take yourself off mute and just hop on in. There's not that many people to manage. So, okay, so let's start with why like real full-scale problems, whether they're natural hazards or not, kind of feel different from a textbook kind of problem you're sort of accustomed to from the undergraduate days and master's level work. And they're kind of obvious, but we should probably, enumerate them. These problems, most real problems are poorly posed or poorly defined to start out with. You're often limited with sparse or even biased data that has to get untangled before it's of any use. A good example of biased data is looking at insurance claims data after hurricanes. There's all sorts of filtering that needs to be done before the dollars and cents in that data actually makes any sense. So data management and data access are huge drivers for how you frame a problem. Usually we're talking about very nonlinear and interacting multiple systems that can throw simplifying assumptions and models right out the window, or drive you screaming towards those simplifying assumptions to make it manageable. And it kind of just depends on your circumstances. Most problems that you'd want to solve as an engineer or researcher have real societal consequences potentially, right? So that makes it a lot different than a textbook problem of how many inches did my cantilever beam deflect, right? And there's almost never a single correct answer, which means there's plenty of career to be had for everybody. It's kind of the good news there. And of course, reality is quite messy. And I'll show you a picture from my field. Anyone want to guess what that's an aerial view of?
A residential area, I guess.
It was a residential area along the coast of Mississippi after Hurricane Katrina in 2025. And it was, Katrina was about a category 3 in terms of wind speed, but a category 5 in terms of surge. So what you're seeing is the first quarter of a mile of the coastline of Mississippi. The first quarter of a mile from south to north is entirely eliminated. You see blank slabs. And you see that debris line? That's where the elevation of the ground made stop the surge from coming any farther north. So you see houses that are still standing just barely north of it. This is a messy problem to frame and to decide what your problem statements are going to be. So this is a motivator, and this is the one, replace this with your own hazard image as we go through. So what I'm going to try and do, in about 20 minutes or so is we'll talk about framing open-ended problems, make some decisions about what to include and exclude, or talk about the need to do that. learn how to build solutions from first principles instead of jumping right at the solution or to your favorite CFD model. You kind of have to start with, even drawing out simple concepts. Formulating strong research questions. Whether we're talking about writing a paper that's going to get published or a dissertation chapter that's going to resonate with your committee or a proposal to NSF, the strong research question is a really important thing to anchor yourself to. And I'll give you an example of a vague question, and then we'll refine that over the course of the talk. And then we're going to apply these things in a short exercise that we'll do together individually, so to speak, at the end, if I haven't kept babbling past the 1:30 mark. All right. So let's start with an intentionally bad problem statement, or I should say vague or incomplete problem statement. You've probably all seen things like this before in papers and proposals and so on. So I'm going to estimate hurricane damage in Florida. Sounds good. Someone offer me an example of why this is a failure as a problem statement. I've got a list that follows, of course, but go ahead and shout something out if you can think of it. I'll get you started. Spatially and temporally unbound. What do you mean by Florida? Just the coast, inland, the entire state? Is that feasible? Temporally bound, estimate hurricane damage. Next year, the past 20 years, the hurricane that just made landfall. So much is left to be identified in this problem statement. It's not really a problem statement. The hazard is ambiguous. A hurricane's got wind, surge, flooding, heavy rainfall, tornadoes, right? So estimate hurricane damage from what about the hurricane? It implies no method or metrics. What do you mean by damage? Is this insured losses? Is this dollars and cents? Is this physical damage to residential infrastructure? Is it how many windows broke in high-rise buildings, right? It's undefined. There's no stopping point. It kind of goes to the temporal unbounding in the first bullet. But you got to, box yourself in about the time frame you're talking about or a specific event or projecting. And so this idea of it being an open-ended question, don't let that prevent you from scoping and defining the problem, right? It's actually your job to close the open ends. If you write, again, motivationally, it's a dissertation chapter, it's a proposal, it's a paper you're writing, it's a research meeting with your faculty member, right? Open-ended isn't supposed to stay open-ended. Scoping is freedom to define what you mean by estimate hurricane damage in Florida, right? Don't think of scoping and refining as a limitation or a weakness. It's strength. We can start, by the way, so most of the rest of these slides have to do with sort of refining this intentionally bad problem statement. We have to start by clarifying the core purpose of what it is that we want to do. Right? So what decision or understanding is being sought? Who are the stakeholders? Stakeholders can mean a lot of things. Stakeholders are the people who will be impacted by or informed by the research, right? So stakeholder could be homeowners. Stakeholder could be emergency management in Florida government. It could be policymakers, lawmakers. It could be the insurance industry. Which directions you take your scoping will change different groupings of stakeholders. And that's always your audience. You have to speak to your audience, just like any other technical communication. Have a good idea what success looks like. This doesn't mean what are the numbers, what are the answers. It means if I'm able to get, the quarter, the bottom quarter of Florida predicting its inundation risk within 50% accuracy over the next 10 years. I've made all that stuff up, but I'm defining for myself what a successful outcome could look like. And that should be a part of your core purpose. So an example, take that statement on the previous page and refine it and say, I want to understand how wind and building uncertainties affect residential damage. And I'm going to quantify that as physical exterior components. Notice what we've changed. We didn't solve the problem, we made it purposeful. Right? Once your purpose is clear, the scopes and the decisions become defensible instead of arbitrary. You want everyone to understand the direction you're trying to go. A good place to start once you've kind of got that refinement of your problem statement is have a good think about what you already know, what is uncertain, and what you anticipate to remain unknown. And known means you know enough about it that you can kind of put a pin in it. So I'll give you some examples. These are not cast in stone. You may argue with these things. That's the idea. Just the thought process is an example of the knowns for this hurricane situation is if we're talking about a specific hurricane that made landfall, say Hurricane Michael, we have a pretty good idea of the wind structure physics, right, from atmospheric modelers. And we have a pretty good idea because we're looking back in the past of what the track of that storm was. We have a pretty good idea of how wide the wind fields were. What is still uncertain, and trust me, this is true, the specifics or refining the near surface wind speed, near surface where the buildings exist that are actually causing the damage. The specifics of the terrain effects that are surrounding the individual buildings are still uncertain, not unknown, but there's uncertainty. And the building attributes. If I'm looking at a large volume of thousands of structures, I'm not going to look at them all personally. I'll never know necessarily how many hip roof buildings there were or how many were built to which building code. We have to incorporate the idea that this is uncertain when we're formulating our problem statement. And things that are unknown, like construction quality, that picture I showed you where those houses are no longer there, I will never know what kind of nails were being used to connect the trusses to the roofs, for example. Localized wind effects, human required mitigations. I don't know if the people went and put shutters on their windows before the storm, if the house is gone, for example, right? So again, I should have put that picture up first, just as a reminder. Just looking at that picture is a guideline to asking, what do I know? What is uncertain? What is unknown? Scoping now is a design choice. I said it before, it's not a limit. It's not a weakness. It's a tool. It's not something you apologize for. It's an explicit scope improves the rigor of your research. So an example scope could be the scope of my research is going to be wind only hazard. I'm going to stay away from the storm surge. I'm only going to focus on single family residential because those are prescriptive codes and they're not engineered, so they would behave very differently than a 5-story concrete frame building. I'm only interested in coastal regions of Florida that weren't inundated by surge. And I'm going to focus on roof damage as a metric, right? Your scope doesn't have to be any of those things, but that's an idea of adding layers to my scope of interest for this problem. Then I have an explicit discussion about what to exclude. I'm not doing storm surge. I'm not doing flooding. I'm not interested in monetary losses. I want physical damage losses, right? Things that I'm leaving out of this list could be, are we going to look at interior damage, right? You don't want to exclude elements of your scope because you didn't think about them. You get out into the field and start quantifying damage with this fancy app that you developed your survey in. And then you realize, oh, I could have gone, most of the people out here that I'm inspecting the damage are inviting me into their house to see the interior damage. There's nothing on my form about interior damage. That's a big missed opportunity because I never even thought about whether I should include or exclude that component of the problem statement. Don't start with your favorite software or your favorite model. Before choosing a model, determine the physical chain of causality, right? And another way of looking at that, if you are a CFD modeler, for example, make sure you don't look around for things to hit with your CFD hammer. You've heard that phrase before, right? If you want to do a CFD project, make sure you scope the project to be appropriate for that tool. And I'll give an example of when it might not be later. So understanding the physics and chain of events. So for this problem we're talking about, starting with the wind, that creates pressure when it interacts with the structure. That pressure creates a demand or a load. That load is then felt by the components that may or may not result in failure, and that failure gets quantified in a certain amount of damage, right? That is going to help me decide what kind of tools I'm going to need and refine the uncertainties in the problem. This list is from left to right, but the best illustration I could find goes from right to left. So sorry about that. But for the wind folks, this is the classic Allen G. Davenport wind loading chain. And this defines from right to left the wind and the pressure and the demand. And then the last two, the failure and the damage, are then going to be defined by the way that building is put together, right? Understanding all of those components is pretty darn important before I decide on a model or the number of models that have to interact with each other. Choosing model complexity is really important. Does the data support the sophistication of your model? Are you making too many assumptions that you can't justify? Does the complexity change the conclusions? I'll give you an example in a moment. So I could use a much more sophisticated model, but would it actually lend itself anything to additional validity or findings? Can I explain and defend my choice of models that I'm using? For example, again, our roof cover damage prediction problem. If the way I choose to model the wind interacting with the structure stops at, let's just stop with getting a good idea of what the mean wind speed was in an equivalent open terrain environment. Is that a sophisticated enough model for me to start predicting roof cover damage? I made it orange because it's almost red, which means, nah, it's not really good enough. I wouldn't accept this as a sophisticated enough model of the wind part of the problem statement. If I got more sophisticated and say, well, I'm going to use some gust factors that give me an idea of the peak wind speeds riding on top of those means, and I'm going to take into effect that a home in the middle of a dense suburb is different than a home next to a Walmart parking lot. Well, now I'm getting good enough sophistication on my wind model to be able to relay that back reliably to the performance of shingles. So I could take it up much more complicated than that. I could have an entire neighborhood or region and try to come up with a full transient computational fluid dynamics model of that. Would that add insight to my ability to predict within a reasonable uncertainty the performance of roof cover? I would suppose in this case the answer is no, for a lot of reasons. Not that CFD isn't a useful tool, but using CFD for this kind of thing would open up way more questions than it would offer solutions. Right. So I didn't go for the big guns, the CFD. I kind of pared back the models that were appropriate for my problem statement. Defensibility over elegance. You want to prepare yourself to be able to answer to your audience, whether it's your committee, your dissertation committee, or a conference, the audience at a conference or whatever. Why did you choose this hazard representation? Why this spatial resolution? And kind of making stuff up. Why these assumptions that you've presented? Have an answer for all of these things and use it to inform what you do, not just after the fact. Justified assumptions matter more than sophisticated tools. What I mean is the simple model you can defend beats an elegant model you can't explain. I can give you lots and lots of examples of people who embarrassed themselves by using complicated models. Someone asked a simple question in the audience about how it worked and they had no idea, and their credibility went right out the window, right? And here's a secret if you haven't discovered this already. Proposals, papers, thesis defense, your audience will attack assumptions or lack of assumptions. They almost never attack equations, right? So put yourself in a box and define it cleanly by your assumptions. So here's sort of a summary ground up engineering workflow to kind of put together the stuff we talked about so far. We're going to define the objectives and the audience. Again, that's the stakeholders. Who are you talking to? What are you trying to convince them of? Conceptualize the system like that wind load damage chain that we talked about. Be familiar with the physics as best you can. Identify the dominant mechanisms, whether it's wind or surge or the capacity of the nails holding the shingles down to the roof. Choose the simplest adequate model. We kind of went through that illustration earlier. State your assumptions very explicitly, the stuff you're doing and not doing. And then you're in a position to validate, iterate, improve, and defend what you're doing. Most important audience when you're defending and improving is yourself. It's hard to fool yourself unless you explicitly let yourself fool yourself, right? So here's our exercise. We can do that. The idea is I put up this challenge and we spend a couple of minutes on our own and then we, talk about what you come up with. So here's the scenario. It's pretty much a repeat of what we've talked about, right? A coastal Florida community is impacted by a major hurricane. After the fact, you approach NSF for what's called rapid funding. This is money that's available very quickly on very short notice for very specific purposes to do work related to perishable data. So if you go to NSF and say, I just want to study the hurricane, they're going to say, yeah, no, you need to refine that. You need to scope, right? So here's what I want you to do. We're not going to do the whole thing. I just want you to do a couple of simple steps. Define a specific scope. the hazard, the infrastructure, the metrics, the outcomes that you're interested in. Just write something down or think of it. Then name just one explicit thing that you're going to exclude from your scope and have a reason why, right? Could be anything. And then write an impactful research question. So I'm going to give you, we have 7 minutes left according to my clock. So I'll give you a minute and then I'll start asking for volunteers to throw stuff out. And then I've got my own version of the solution on the next slide. But who's got an idea for number one? Who wants to define a scope?
I can go.
Sure.
I chose infrastructure because I wanted to focus on what the damage, what the hurricane damage is done to like infrastructure, so like the buildings basically, and for like
Okay.
those are the two things I'm focusing on.
So if I were drilling down then, if I were starting there, I would then ask if we were a research team deciding to collaborate. By infrastructure, there's natural infrastructure, there's man-made infrastructure, there's transportation infrastructure, there's residential infrastructure. So then we'd have a conversation about, are we talking about the mangroves that line the southern part of Florida as the natural infrastructure or residential or whatever? So that's the next thing. But that's a good start. You decide to focus on infrastructure. Anyone else had something you came up with that was a little different? What about an explicit exclusion? What are we not going to consider in the big picture? I guess we should stick with Zul since she volunteered. Did you come up with one?
I think one thing that I would not one thing I would exclude would be the monetary value
Okay.
because I feel like it will complicate it. Like if I'm sticking with man-made infrastructure, say like housing, for instance, I would want to exclude what the monetary impact would be just to kind of streamline what my focus is on. It would be more on the scientific side and yeah.
Yeah. And when you're sitting around with people and colleagues who might have a little bit more experience, I would say that's a really excellent exclusion because the monetary aspect has to follow an understanding of the physical damage aspect, which is really where we should start. And the monetary aspect is a whole nother animal that involves actuaries and financials and stuff we as engineers don't have much of a grasp of. So excellent exclusion. What about an impactful research question?
I
One,
would say I haven't been able to come up with it. I'm in the process of coming up with it, but
okay.
it's much more difficult than I thought.
Oh yeah, yeah, and the idea is just to get your mind started through those steps, right? And of course, it'll take more than 1 minute in reality. So here's my example answers. I just kind of followed the path of what we did before. My scope is going to be wind-induced roof failure of residential construction, or a different example could be surge-driven inundation of slab-on-grade structures. Um, then my exclusion was going to be interior damage, dollar loss, just like you, and power outages. So lifeline type damages, which is another really important aspect, is an entirely different animal. How many light poles fell over is a whole different question than how many houses lost their roof, right? So we're excluding things so we can focus on one thing. The research question I came up with is just a repeat. How does uncertainty in near surface winds influence predictability of roof failure probability in coastal residential buildings? Remember where we started. Estimate hurricane damage in Florida. We've come a long way, right? That research question is what I give to the rapid program officer at NSF. What I've done is taken a big problem statement like this wider out aerial view of the impact of Katrina and narrowed down on houses that still exist that are exhibiting roof cover damage. That's what I'm going to zone in on. Takeaways. Last slide. Open-ended problems are normal and they're the reality. So it's a good thing we're talking about this stuff. Framing determines the success more than the tools you use determine the success. Only when those two things match do you get a success. Scoping enables rigor, defensibility, impact, quality, allows you to define exactly what it is that you want to research and what your intended outcomes are. Strong research questions align the purpose, the people, stakeholders, sponsors, homeowners, methods, and contributions that you're making. The big takeaway, when your research or approach feels messy, and overwhelming? The answer usually is you need better framing, not necessarily more complex modeling. Could be both. All right. Back again. We got 2 minutes for questions, but if you did want to do more sufficient, more detailed follow-up, I'm always very eager to answer emails and have side conversations. So please let me know.
Oh, I do have a question.
Yeah.
So, if you have already determined a methodology that you want to use to solve a problem, how do you kind of define the problem?
Yeah. So that's kind of like if you're I said earlier, if you're a CFD modeler and you're looking for a way to insert your expertise in hurricane hazard, you do apply many of the same principles, but you kind of go at it from a different direction. And how do the knowns and the unknowns and the uncertainties influence whether your model is appropriate? If it doesn't match, you change the problem statement so that the knowns, the unknowns, and the uncertainties are a better match for your model. So right, you don't have to force a round peg into a square hole, but if you want that, if you want to use that round peg, you got to search for the round hole, right? So yeah, perfectly legitimate that you predetermine the tools you want to use and you're looking for a proper application. It's like I tell students in my structural analysis and design courses, designing and analysis are exactly the same tools. You just start with different givens and you have different goals, right? But it's same statics and equilibrium and physics.
Thank you so much.
Anyone else? Yeah, you see my I'll put my email in there as well. Yeah, feel free to reach out. Just
Can
put
we
in your
also
sub just
connect
put in your
with me?
subject, Robin sent me, and I'll respond.
Can we also connect with you on LinkedIn?
You can. I'm pretty much an amateur at all manner of social media, but I do have a LinkedIn account that I'm being told by my marketing communications director that I need to learn how to use. So, but yeah, I do have a LinkedIn account. I do have connections, so you can certainly reach out that way. If I don't respond that way, I probably just don't have my notifications on or ignoring them. So email me if I don't respond to your LinkedIn.
Does anybody have any other questions? Thank
I,
you so much. Oh, you wanted to say something?
I was just going to say thanks everyone for attending and good luck on whatever.
Thank you so much for the wonderful presentation. I know I learned a lot because I also have a similar problem of trying to work backwards. I have a methodology, a tool, and trying to understand what problems I'm trying to solve.
Yeah. Well, I'll say like this whole idea of open-ended to something you can do is very much like my experience with editing my writing down to something that's good, right? You start with a lot and you keep on removing and removing and removing until it's what you want. It's like a good sculptor says, carving the statue of David was easy. I just removed all the stuff that wasn't David. So that's what we're doing by scoping down an open-ended problem. All right, I got to scoot to another meeting. See you guys.
Thank you so much.
Thank
Bye.
you.